Hello again. We are moving on to another chapter of Algebra 1. We are talking about not just one linear equation, but we're talking about multiple linear equations going on at the same time on the same graph, and those are called systems of equations. We're going to talk about how to solve systems of linear equations in many ways, but the first way we're going to talk about is by graphing them. So let's get started. Let's define a few things first. A system of equations is basically just what I said. It doesn't have to be linear equations, but in our case, that's where we'll start. But more generally, it's two or more equations, and each one of them has multiple solutions. Okay, and a solution to that system is going to be any set or sets of coordinates that make all the equations true. So I could plug in that x and y into all of the equations, and it would make all true statements out of all of them. Okay, so a consistent solution is going to be one that has at least one solution. So if the equations cross at least once, or the lines or graphs or whatever, if they cross at least once, then we can say the system is consistent. Even more specifically, if a system is consistent, it can also be independent, meaning that it has exactly one solution. Or if it's consistent, it can be dependent, and it can have infinitely many solutions, meaning it crosses everywhere. The two or more graphs, or however many you have, they're all the same and they overlap each other everywhere. So it's like having the same graph on top of itself twice or more times. And then lastly, if it's not consistent at all, if it doesn't have at least one solution, that makes it inconsistent, and that means it has no solution. Okay, so let's talk about how to solve systems of linear equations by graphing. So we're going to graph each line separately on the graph, and we will have enough information. We've had enough practice to do that. We're just graphing multiple lines on the same graph instead of just one. And so we just find the point where those lines cross. And then that's going to be the solution to our system of linear equations. Okay, so one thing that can happen with lines is that they can cross once, which means that the system is consistent and it's independent, and there's just one solution. The second thing that can happen is that the lines don't cross because they're parallel. And that means there's no solution. There's no point where they cross. There's no x and y that's a solution to both lines at the same time. And then the third thing that can happen is they overlap everywhere. It's basically the same line on top of itself. And we can say that that system is consistent and it's dependent because there are infinitely many solutions. Okay, so those are the three things that can happen. So let's take a look at an example of each one. First, I've got y equals 3x minus 5, and then x plus 2y equals 4. We're going to graph both of those on the same line, starting with y equals 3x minus 5. I know that y equals 3x minus 5 has a y-intercept of negative 5, and it has a slope of 3. So if I find negative 5 on the y-axis, I can plot a point, and then I can use the slope of 3 to find a second point, and I can graph that line. The second line I can use, it's in standard form, so I can find the x-intercept and the y-intercept. So the x-intercept is 4 and the y-intercept is 2. I can find those on each axis and join those with a line. And so now I can see that the lines cross exactly once. So the system is consistent and independent because it has one solution. Well, what is that solution? It's 2, 1. X equals 2, y equals 1. That is the x and the y that I can plug into both equations, replace those letters with those numbers, and it would make a true statement for both of them. There's no other x and y that would work that would be able to do that. Okay? That's why I say I only have one solution. So here's another example. If I have y equals negative 2/3 x minus 2 and 2x plus 3y equals 6, if I look at the first one, it's in slope-intercept form. The y-intercept is negative 2, so I find that on the y-axis, and I use a slope of negative 2/3 to find a second point, and I can draw the line. For the second one, it's in standard form, so I find the x-intercept and y-intercept. The x-intercept is 3, the y-intercept is 2, so if I plot those points on the right axes and then join them, I've got my second line. And as you can see, these two lines are parallel. They have exactly the same slope. So what that means is they're never going to cross. So I can say that the system is inconsistent and has no solution. So there's really no x and y that I could plug into both equations and create two true statements. Okay, so there's no solution to a system that has parallel lines. And for the last example, I've got y equals 4/5 x minus 4, and I've got 8x minus 10y equals 40. So the first line again is in slope-intercept form. It's got a y-intercept of -4, so I just find -4 on the y-axis, and I use a slope of 4/5 to find a second point, and I can draw a line. The second line is in standard form, so I find that the x-intercept is 5 and the y-intercept is -4, and I plot those points, and I draw the line. And it looks like I've drawn exactly the same line twice. So what that means is, since the lines are exactly the same line, just written in two different forms, the system is consistent because it has at least one solution, but it's dependent because there are infinitely many solutions. So any xy that would be a solution to the first equation is also a solution to the second because they are exactly the same line. All right, so those are examples of the three things that can happen when you are graphing systems of linear equations. If you have any questions, please let me know, and I will see you tomorrow.